section, we'll talk about the t-distribution. As we'll see, the t-distribution is similar to the normal distribution, but it has some important differences. We use the t-distribution when the standard deviation of the population is unknown. But first, a quick review of normal distributions. 5% of the area of a normal distribution is more than 1.96 standard deviations away from the mean. Therefore, 95% of the area is within 1.96 standard deviations of the mean. Therefore, if we randomly sampled a value from a normal distribution, the probability that it would be more than 1.96 standard deviations from the population mean is 0.05. We are often interested in means rather than single values. Calculations about means are based on the sampling distribution of the mean. Recall that the standard deviation of the sampling distribution of the mean is called the standard error of the mean. Therefore, the probability that a sample mean is more than 1.96 standard errors from the population mean is 0.05. But what happens if we have a normal distribution and don't know the standard deviation? We would take a sample and compute the sample mean and sample standard deviation. We could then estimate the standard error of the mean based on the sample standard deviation and the sample size. But how do we determine the probability that our sample mean is more than 1.96 estimated standard errors from the population mean? This isn't easy since there are two factors that affect whether the sample mean is more than 1.96 estimated standard errors from the population mean. 1, the value of the sample mean, and 2, the estimated standard error. The probability of a sample mean being more than 1.96 estimated standard errors from the mean is higher than the probability of being 1.96 actual standard errors from the mean. But how much higher is the probability? Lucky for us, someone else, namely William S. Gossett, has done the hard work and solved this problem. While working for the Guinness Brewery in Ireland, he managed to work out the distribution of a mean divided by an estimate of its standard error, saving us a lot of headaches, but maybe giving himself some in the process. This distribution is called the student's t-distribution, or sometimes just the t-distribution. Why not the Gossett distribution? Well, it seemed that his contract with the brewery prevented him from publishing under his own name, so he chose the pseudonym Student. The t-distribution is very similar to the normal distribution when the estimate of variance is based on many degrees of freedom. But when there are fewer degrees of freedom, the t-distribution has relatively more scores in its tails. You'll learn more about degrees of freedom in a later section, but they basically refer to how much information an estimated standard error is based on. The number of degrees of freedom is determined by the sample size. This figure shows the t-distribution with 4 degrees of freedom in blue and the standard normal distribution in red. With 4 degrees of freedom, the t-distribution has relatively fewer scores in the center and more in the tails. This means that the t-distribution is leptokurtic. Because the t-distribution is leptokurtic, over 5% of the distribution is more than 1.96 standard deviations from the mean. This table shows the number of standard deviations from the mean beyond which remains 5% and 1% of the area. Note that these values are different for different degrees of freedom. The fewer the degrees of freedom, the farther you have to go in both directions to contain 95% of the area, and thus leave 5%. For example, you have to go 4.3 standard deviations in both directions for 2 degrees of freedom, and less than 2 standard deviations for 100 degrees of freedom. Notice that with only a few degrees of freedom, the values of t are much higher than the corresponding values for a normal distribution. Also notice that, as the degrees of freedom increase, the differences between the corresponding values for the t-distribution and the normal distribution decrease. Let's think about an example problem. Suppose we sampled 9 values from a normal distribution and estimated the standard error of the mean. What is the probability that the sample mean would be more than 1.96 estimated standard errors from the population mean? First, we determine the degrees of freedom. The formula, which you'll hear more about later, is n-1. Our sample size is 9, so we have 9 minus 1, which equals 8, degrees of freedom. The t-distribution calculator can then be used to find that with 8 degrees of freedom, 8.57% of the area of a t-distribution is more than 1.96 estimated standard errors from the population mean. Recall that this is more than for a normal distribution, where 5% of the area is more than 1.96 standard deviations from the population mean. Suppose we want to know how many standard errors from the mean is the 5% cutoff. That is, the cutoff point that would leave 5% of the area of the t-distribution in the tails. We know that the area in the tails is too big if we use 1.96 standard errors, so we use the t-table to find out where our cutoff should be. Using the t-table, we can see that with 8 degrees of freedom, we need to use 2.306 estimated standard errors as the cutoff in order to have 5% of the area under the curve in the tails. As a side note, you may be wondering what is so special about the 5% value. As you'll see in a later section, this is a conventional value used in inferential statistics. In conclusion, the t-distribution is used in place of the normal distribution whenever the standard deviation is estimated. Its shape is similar to the normal distribution, but has more scores in its tails. As the degrees of freedom increase, the t-distribution becomes more similar to the standard normal distribution.